Hola a todos. Bueno, quería también comenzar dando las gracias a la SEA por este premio, que ha representado una motivación extra para mí para seguir adelante en mi carrera investigadora. Y la tesis de la que voy a hablar se realizó en la Universidad Autónoma de Madrid, bajo la dirección de Rosa Domínguez Tenreiro y Chris Brook, a quien también quiero dar las gracias públicamente por su supervisión y su confianza en mí. Y también extender las gracias a mis colaboraciones y las personas que contribuyeron a mi tesis. Voy a dar mi charla en inglés. The title of my thesis is Dwarf Galaxies in ΛCDM. And why dwarf galaxies? By definition, dwarf galaxies are dark matter-dominated, low-mass and low-metallicity galaxies. However, apart from that, one could say that each dwarf is unique. So, for example, here I'm showing some dwarf galaxies from the local group, where we can see that they have very diverse properties. For example, diverse sizes, morphologies, star formation histories, internal mass distributions, etc. Some of these properties disagree with the basic predictions from lambda cold dark matter, which is our standard cosmological paradigm. Therefore, dwarfs are interesting to study from both the point of view of trying to understand galaxy formation mechanisms, but also from a more fundamental point of view, as they can serve as proofs of our cosmological framework. In my thesis, I have studied some of these puzzle properties observed in dwarfs within a cosmological context. My main tool have been the use of zoom-in cosmological hydrosimulations of galaxy formation. These are zoomed-in regions of large dark matter-only volumes that are resimulated at high resolution, including the physics of gas and star formation. In this way, central disk galaxies, like the one you can see, are simulated with dwarf galaxies around them. In particular, during my thesis, I made use of simulations from the projects listed here below. The first part of my thesis was dedicated to studying the distribution of mass in dwarfs. In particular, in the context of the diversity of dwarf galaxy rotation curves. The issue here is that ΛCDM predicts a unique rotation curve for dwarfs of a same mass scale. However, we observe rotation curves with a diversity of rotation curve shapes. Here I'm showing 4 dwarf galaxies that have a similar mass, for which ΛCDM predicts the rotation curve shown as a black line. However, some of them rise more steeply in the inner regions, some are compatible with the prediction, and some rise very slowly. The first case, the ones that rise steeply, because the circular velocity is proportional to the mass enclosed, these steep cases could in principle be explained by the accumulation of variance in the inner regions. These are called cusps, or cuspy rotation curves. However, the cases where the velocities are below the ΛCDM expectation imply a deficit of mass, or a core in the dark matter distribution. One way of producing diversity is considering that galaxy formation processes within ΛCDM can modify the inner dark matter distribution of galaxies. In particular, galaxy formation models that include detailed recipes for stellar feedback, like for example, supernovae explosions or feedback from massive stars, can produce outflows of gas that push outwards the dark matter particles and expand the halo. This can lead to the formation of cores in dwarf galaxies. But more generally, this produces a complex baryonic cycle that can lead also to the formation of realistic simulated galaxy populations in general. Here are some examples of the diverse rotation curves of simulated galaxies from the MAGIC project that has a galaxy formation model as that kind I was explaining. This galaxy is a dwarf galaxy with a slowly rising rotation curve, and these other two are more massive galaxies with cuspier rotation curves. A way of probing these rotation curves and if the mass distributions they imply are realistic is through the mass discrepancy acceleration relation. Mass discrepancy refers to the difference between the total mass in a galaxy and the baryonic mass enclosed at a certain radius. And the acceleration is basically the velocity squared over radius, and given only by the baryons. In this figure, each point represents a point along a rotation curve and is read from right to left. Although there are lots of galaxies plotted in this figure, in general, they fall on one main single trend. We used the magic galaxies and showed that this main trend was also reproduced within lambda CDM, proving the realistic mass distributions. Furthermore, we showed that the scatter that we found, the points that fall below the main trend, were given by points corresponding to the inner regions of rotation curves of slowly rising rotation curves, like this dwarf galaxy, for example, here. This was the first time that this relation was reproduced within lambda CDM, the lambda CDM simulated galaxies. And this was also relevant because this relation has been used by some authors as a claim against cold dark matter and favoring alternative models like modified Newton dynamics. Another relevant result that we found was that the most slowly rising rotation curves observed were reproducible within lambda CDM. Here I'm showing in red the rotation curve data of two galaxies, the two observed galaxies that have the largest cores. And in gray, rotation curves of two galaxies from the Nihao project, a project of simulations that allows the dark matter halo expansion due to stellar feedback. The agreement, as you can see, is very, very good. This agreement was also found because we computed the circuit velocities using the true gravitational potential instead of assuming spherical symmetry. Therefore, we were able to show that cores are not a problem for lambda CDM. However, the cuspiest cases, the galaxies with the cuspiest rotation curves, are still not reproducible within these kinds of models. And this is something I have explored further during my postdoc here at the University of Victoria, focusing mainly on the contribution of baryons to the velocity. And we find that for the moment, no model is able to recover the full range of the diversity in rotation curves observed. So this remains an open issue. A second project of my thesis concerned dust emission in dwarf galaxies. In particular, recent Herschel observations of dwarfs showed that they had special and diverse spectral energy distribution shapes, especially in the infrared region. These special features can be summarized in a low intensity of polycyclic aromatic hydrocarbon bands, an excessive emission in the sub-millimeter region, and a broadening of the infrared peak of the SED. These infrared features are pointing towards special dust emission in dwarfs. And so modelers have invoked the need for extra dust components, but there's not a physical motivation behind them. To study this, we made use of the state-of-the-art radiative transfer code for SIL3D that has been proved successful to study massive galaxies. This code includes a very detailed treatment of dust, in particular distinguishing between two phases, a dense phase associated to molecular clouds that are heated by young stars, and a more diffuse phase associated to cirrus that is heated by old stars. My contribution to the code was to adapt it to include the specificities of observed dwarfs, in particular the power law dependence between the dust to gas mass ratio and metallicity, and also the low abundance of PAHs. We interfaced this code with star-forming dwarfs from a clue simulation. Clue simulations include initial conditions that allow the formation of a large-scale structure like the local universe, and also the formation of a Milky Way Andromeda pair. The result that we obtained was that we were able to recover the diversity of spectral energy distributions observed. And more importantly, we were able to give an explanation, a physical explanation to it, which is given by the behavior of molecular cloud emission. In particular, if molecular clouds absorb a high amount of energy because of the presence of those stars, they dominate the emission, as shown here, broadening the infrared peak, hiding the PAH band emission, and producing an excess of some millimeter emission. Finally, I will talk about a project that represented the bulk of my thesis, the second half, which studies the problem of the planes of satellites. Satellite galaxies in the Milky Way are spatially organized in a planar structure that is mostly perpendicular to the galactic disk. Also, young globular clusters in the halo and some streams align with this structure. Moreover, thanks especially to recent proper motion data from Gaia, it has been shown that some of the satellites are co-orbiting within the plane that they define in position space. On the other hand, in Andromeda, there is also a thin plane of satellites, shown here in red, formed by a group of objects that have a somewhat coherent radial velocities, which suggests that they may be also co-orbiting. However, these planes are not common in dark matter only large volume simulations in ΛCDM, and therefore this has led some authors to say that this may be one of the most severe small-scale problems for ΛCDM. My motivation, therefore, was to understand if planes of satellites could be formed in hydro simulations of disk galaxies like the Milky Way, and if so, what were their main trends. We developed a method to identify planes of satellites from position data, a method that could be applicable both to observations and simulations. This method consists in fitting a plane to every combination of 4 satellites and projecting the normal vectors of these planes onto the sphere. With these projections, we build a density map like this one and identify the high density peaks. These peaks are pointing in the direction of predominant planar alignments of satellites. Satellites are then ranked by their contribution to normals in the direction of the peaks. And we fit the plane to increasing groups of satellites following this order. So we fit the plane to the 7 satellites that contribute most. Then we add 1 satellite at a time and we repeat the plane fitting process until we use all the satellites. In this way, for each of the overdensities found, we have a collection of planes of satellites that defines that planar structure. The application of this method to observational data has allowed to better characterize the planar structures in the Milky Way and in Andromeda. In particular, we find that the plane in the Milky Way is one structure that is perpendicular to the disk. Our method also allows to study how the thickness of the structure varies as a function of the number of satellites involved. We measure thickness through the C/A ratio, which can range from 0 to 1, 0 for perfect flat planes and 1 for a spherical distribution. So what we find is that even when including the total number of satellites in the Milky Way, the planar structure remains thin with low values of C/A. In Andromeda, on the other hand, we find 2 overdensities that are separate almost 90 degrees. The first one corresponds to the well-known Great Plane of Andromeda, but the second one is new and hadn't been studied before. These are 2 different structures and they are perpendicular to each other. We observe that these 2 planes have similar thicknesses up to, let's say, around 18 satellites each. However, the thickness increases as we add more satellites to the plane. This is because these planes, as I said, are perpendicular to each other, which we can see better here in this view where I rotated the system such that we could observe both of the planes edge on. We applied our method to 2 simulations of disk galaxies, PDEVA 5004 and Aquarius C alpha. These are Milky Way type galaxies that have thin stellar disks, a high number of satellites, and the quiet merger history. In this figure, I show the thinnest plane of satellites found at a given time, including a certain fraction of satellites. For example, the dark blue line shows the thinnest plane, including a 90% of the satellites. This is almost the complete satellite population of the time. So what we observe is that during the whole evolution of the system, almost all the satellites are distributed in a planar structure, as the C/A value on average is low. Moreover, there are some periods that I have marked with this shade where the plane is especially thin. These periods correspond to times when the planes are mostly perpendicular to their central disk galaxies. Therefore, we showed that in general, satellites are organized in planar structures around disk galaxies like the Milky Way. But are these planes long-lived? Are they persistent in time, like seems to be the case of the plane in the Milky Way? To study this, we introduced into our methodology another variable, the orbital angular momentum. By analyzing the clustering of orbital poles, the projection, here is an example of the projection of orbital poles on the sky, we were able to identify groups of satellites with aligned orbital angular momentum vectors during long periods of time. These co-orbiting satellites were shown to be statistically different from the rest of satellites in the system. In particular, they have a higher specific angular momentum, they are orbiting at larger radial distances from their host, and more perpendicular to their central galaxy. We fitted a plane to the positions of these satellites, of these co-orbiting satellites, and could see how the thickness of the plane they form in position varies with the time evolution of the system. We find that both the group of co-orbiting satellites represents a thin planar distribution in position at all times, and the planes are mostly perpendicular to the disk as well. Here's an example of what the plane of satellites looks at this particular moment in Aquarius C. The satellites are very well aligned, and the orbital angular momentum vectors shown as blue arrows are perpendicular to it. The next step is understanding what is the origin of these co-orbiting satellites. Here I'm showing the video of the evolution of the Aquarius C alpha system. The gas particles are shown in blue, and the co-orbiting satellites in red. These satellites, which originate at any place at high redshift, follow the main directions of mass collapse and fall onto the cosmic web sheet where mass is accumulating, which we observe edge on like this. This is suggesting that the local cosmic web at high redshift is leaving an imprint, has left an imprint on these co-orbiting satellites. And because there has been no major merger that can destabilize the system, the satellites conserve their original angular momentum and give rise to a persistent plane of satellites. And I finished here. These are the main conclusions of my thesis. Dark matter halo expansion can recover the largest cores observed. The particular infrared spectral energy distribution features of dark galaxies can be explained by the interplay of a dense and diffuse dust component. We find the second plane of satellites in Andromeda. We find that satellites around simulated disk galaxies are organized in planar structures. And finally, that we are able to identify groups of co-orbiting satellites that define persistent planes of satellites in time and are mostly orbiting perpendicular to the central disk galaxy, as is the case of the plane of satellites in the Milky Way. And that is all. Thank you very much. And here are my acknowledgements as well.
Muchísimas gracias, Isabel. Un aplauso también muy fuerte virtual para ti.
Muchas gracias.
Tampoco tenemos tiempo para preguntas. No sé si Isabel cómo está en Victoria, Canadá. tendrá tiempo para poderse unir al Slack ahora. Esperemos a lo largo de estos 3 días, bueno, pues en algún ratito te pueda conectar y si alguien tiene alguna pregunta, pues ya conversas con él o con ella. Muchas gracias, Isabel.
Gracias.